I can. Oh, yeah.
Maybe I'll take the recording and send it.
Okay. Yeah. Okay. Okay.
All right. So is it okay here now?
Yeah. Yeah. Yeah.
All right. And then so part A is finding velocity. Part B, we're looking for the average velocity over the whole journey. Okay. Velocity for the whole journey. So how can we find the average velocity for the whole journey? Okay. So well, this one actually is easy because I can tell you immediately that the answer is 0. Can you tell me why?
The total displacement is 0.
Yes, exactly. Because the total displacement is 0. Okay, so that's why the velocity is 0 for the whole journey. Okay. See, so we want to find the average speed over the whole journey. Okay. Now for average speed, this time is not 0. Okay, because as I mentioned, speed is just distance over time, right? So distance do not have direction, so you don't have 0 speed. Okay, so this one, we really need to find the distance traveled by the cyclist. Okay, so actually it's not that difficult if you have a displacement time graph, because you know the basically if you think about this picture, it is like it's starting from here and then goes to this position and then it goes back, right? So that means
It's 10
as
over
we
65.
so sorry, can you repeat?
Oh, is it 10 over 65? Because like
10 over 65. 10, where's the 10 coming from? Okay, oh, so 2 times 5,
yeah.
right?
Yeah.
Yeah, 2 times 5 and then divided by if I want the unit to be km per hour, I divide this by 60. Okay, so that means it should be I think it's 9 point around 9.2 if we take 2 SF. Okay, is that okay now? That is
Yeah.
this question.
Yeah.
Okay,
Yeah.
so that's so you need to know how to interpret the displacement time graph. Okay, so so that's one example. So as a remark, just be careful that the sign, okay, because just now you also make a mistake here. You forgot to put the negative sign here. Okay, all right. So this time we're going to go through another type of graph, which is actually very related to the displacement time graph, which is called the velocity time graph. Okay, so as we can think of, well, displacement time graph is displacement against time, right? So velocity time graph is velocity against time. And then let's look at some interpretation or some special velocity time graph. Okay, so for example, if a velocity time graph looks like this, so we have a flat line just on the time axis. What does it tell us about the motion of the particle?
Doesn't move from it. Doesn't move.
Yeah.
Doesn't move from the initial position.
Yes. So the object is just stationary. Okay. Or how about when the velocity time graph is like this? What does it mean?
Also stationary.
Almost stationary. You sure? No, not really, not stationary this time. Because this is velocity, it's not displacement. Now, if this is displacement, then it is really stationary, right? Because it stay in the same position for all time. Then this time is not, because this is the velocity, right? So the interpretation of this is that it is going in a constant velocity. Okay, constant velocity. All right, and then next one will be like this. Okay, how about this one? If a straight line with non-zero gradient, what does it mean? What do you think?
Increasing velocity.
Yes, so that's an increasing velocity. Okay, increasing velocity, or we can say it has a acceleration, right? Now, in fact, this will give us constant acceleration. I'll tell you why. Okay, so first of all, now because previously we have the displacement time graph, right? And then we interpret the gradient of the graph as velocity. So basically, you can think of taking gradient as taking the rate of change. Okay, so that's the very usual way of thinking. Okay, so if you take the gradient of velocity time graph, what will you get? Okay, so gradient is actually the rate of change of velocity, right? Of VT graph is the rate of change of velocity. And then what does it mean by rate of change of velocity? Can I recall?
Oh, is it just velocity over time?
Velocity over time, or what is it called? What is the rate of change of velocity? We have a terminology. Starting with the letter A. This one, right? Velocity, if you take the rate of change, that would be the acceleration. Okay, that's the acceleration. Is that okay for you?
Yeah.
Okay, so gradient of VT graph gives us acceleration. Okay, and then now, did you learn integration? Did you learn integration?
No.
No. Okay. Anyway, if you don't know integration, I think you should not for now. I think you should remember this only. Okay, because I can't really explain very fully why it is the case. Okay. All right. So this so this gradient gives us the acceleration, and how do we recover the displacement? Okay. So for displacement, that would be equal to the now have to be extra careful. I would say it is the side area of VT graph. Okay, so you understand area, you understand VT graph, but you don't know what does it mean by side, right?
Yeah.
So what does it mean by side? Okay. All right. So for sine area, it means the following. Okay. So for example, for your 3D graph, if you have a graph like this, okay, and then the area, for example, the area here is above the x-axis, okay, and this area will give us the displacement, okay, positive. So this is called a positive area, and then it gives us the displacement, okay. But then how about the case when well, if your graph look like this, okay, so as somewhere it goes below the x-axis, okay, so for this area we will say this is a negative area, okay, So that means, for example, if the actual area of this is 2, then we will say that the displacement is -2 over this period of time.
And how do you calculate that area?
Now this one for now is difficult because actually if you have a general curve like this, you will need calculus to do that. Okay, so for now we will just look at some area which is not of a shape of a curve. We will just look at, for example, triangle, trapezium, and so on. Okay, yeah. Is that okay?
Yeah.
Okay, so now, okay, so for example, let's look at the following example here. Okay, so let's say we have a graph, which is like, let's, for example, look at this one. And then let's say this period of time is 2. This period of time is 5. This is velocity, this is time. And then this is 8. This is 0. And then this is 11. Okay. All right. And then our task here is to, first of all, look at the acceleration, okay, at different period of time. And then the second task here is to look at the displacement from t equal to 0 to t equal to 7. Okay, not exactly 8, it's just 7. Okay, so first of all, look at the acceleration. Okay, for acceleration, remember that's the gradient of this graph. Okay, so it is actually different for different period of time. So for example, this one, the acceleration for the first period of time is just for the first journey, that's the gradient. Okay. Maybe let's specify the unit. This is second, this is meter. Okay, so we don't have ambiguity here. So now let's say the first journey, the gradient should be 11/2. So it should be 5.5 meter per second square. Okay, so that's the acceleration. And then for the second journey here, now because this here is horizontal, so that means this for the second journey, the acceleration is 0. Okay, and then for the third journey, here the acceleration should be negative because this is negative gradient. Okay, and then over here is 5 to 8. Okay, 5 to 8. Then so the acceleration should be 11 over 5 minus 8. So it should be 11/3, negative 11/3 meter per second square. Is it okay here?
Yeah.
Okay, so that's the acceleration given but in different period. Okay, and then for the second one, displacement. Okay, so for the displacement, now here is from time 0 to time 7. So it is not exactly finding the whole trapezium. It's just finding this all this area up to here, right? Up to here, which is 7. So I think the main difficulty here is to find, for example, this area or the area of this triangle. Yeah, because you can do it in 2 ways. Of course, you can first of all find the trapezium and then subtracting this triangle, or you can find this trapezium first and then add this trapezium. Okay, I think finding the triangle would be easier, right? So the point is how can we get this height, right? Because we already know that the length here is 1. How can you get the height here? So the trick here is because this is a straight line, right? So that means it should, for example, if you pick any 2 points on this straight line, you should get the same gradient, right?
But it's constant.
Yeah, so the velocity, or you can say the acceleration is constant, not the velocity, okay? So here, let's assume this to be B, okay? All right, then so this, we have 3 points here. We have this 5, 11, B7, and 0, sorry, 8, 0, okay, 8, 0. So if I pick these 2 points and calculate the gradient, that should be identical to if I pick these 2 points and then find the gradient, because this is a straight line. So let's find the gradient using the first 2 points first. And then, but we have found this, right? That's exactly negative 11 over 3, okay? So we have negative 11 over 3 equals to the gradient calculated from these 2 points, okay? So for these 2 points, it should be, the gradient is given by 7 minus 8, okay, 7 minus 8 over b minus, oh sorry, no, I think it's 7 minus 0, right? It's y minus y, 7 minus 0, and then b minus 8.
But 7 isn't the y, it's the x.
Ah, sorry, yes, my fault. It should be 7b, right? Yeah, I've reversed
Yeah,
x
so,
to
so like
my coordinates.
because like you said the acceleration was constant, right?
Mm-hmm.
So 7 should like b should just be 11 over 3.
B should be level 3. Yeah, you can say so, okay, because b over, or if I look at it this from the point of view of gradient, that's just like this. So b is 11 over 3, okay? So now we have found this height here. So we can find the area of this triangle and find this trapezium, okay? And then we do the subtraction. So the displacement, that's equal to, so the area of the trapezium should be that. Now look at this first, okay? So the height is 11, so 11 times the, let's look at the upper base and the lower base. The upper base here is 3, and then the lower base is 8. So 3 plus 8, and then minus the area of this triangle. So this triangle has an area of a half times b times 1. So half times b times 1. So you can get the answer right away. Okay, so this one, it should be, or half times 11 times 3 plus 8.
Should be 352 over 6.
Okay, sorry, can you repeat?
176 over 3.
Over 3, okay. And then the unit is meter here. Is that okay here?
Yeah, I have a question.
Hmm.
No, never mind. Yeah, okay.
Oh, okay. All right. And then that's that's about the velocity time graph. So you need to know 2 things. Okay.
Yeah.
And then another example here, it will be like this. Okay, so we have a particle. So let's write down the description first. Okay, so a particle moves along a straight line. So that's the first condition given. And then first of all, it goes, it accelerates uniformly. Okay, so that means it has a uniform acceleration. From rest to 8 meter per second. Okay, in t seconds. So that's the first condition given, and then it travels for at a constant acceleration. Sorry, constant velocity of 8 meter per second for 5t seconds. That's the second condition given. And then the third condition is it decelerates uniformly. Okay. It then decelerates uniformly to rest in a further 40 seconds. Okay. And then so three parts of the journey. Okay. And then first of all, let's sketch the velocity time graph first. Okay. So the VT graph should be similar to the one I've drawn previously, right? It's just, first of all, it accelerates for t seconds. So it's just look like this. Okay, it looks like it is t here and then 8 here. This is velocity, this is time. And then it becomes flat because it travels in a constant velocity. Okay, and if I already decelerate uniformly, by the way, this is 5t seconds here, 5t seconds here, and then it decelerate uniformly at a further 40 seconds. So this is 40. Okay. All right. So that's the velocity time graph. So that's the part A here. Okay. Part B. So it is given that the total displacement equals to 600 meter. Okay. So here we want to find t. Okay. So here we just refer to this graph and then we find the total area under the graph. Okay. So the
sorry,
total.
Wait,
Yes.
is the displacement just the area of the whole thing?
Yes. So it's the area under the graph because always is positive here. Okay.
Okay. Yeah.
So so here the upper base is 5t. So 5t plus the lower base is t plus 5t plus 40. So t plus 40 plus 40. Sorry, yeah, and then 5t, sorry. And then the height is 8, and then 1/2. That's equal to 600. Okay. So next we just solve this equation. So it's 450 here, and then this is 11t plus 40. So 110 at the right hand side, and the t is 10 seconds. Okay.
Yeah.
All right. So that's the that's the velocity. Sorry, that's the displacement. Okay. And then one more example. So this time we have this one. We were trying. Again, this is the velocity time graph. And then let's say this one, we have this one here, and also one here. And then we also know that, for example, the velocity, the acceleration here equals 2, and then the acceleration here equal to, for example, -1/2. Okay, so these are the conditions given. So let's say, let me give the units here. And then the task again is to find the total displacement. Okay, so this time you have to be extra careful because as I mentioned, this part of the graph is below the x-axis, right? So,
Yeah.
so this one actually gives us, for example, if you add these three areas, you have to add the negative sign here because it is below the x-axis. Okay, so okay, all right. So how can we do this question? So I think the key point is there are a few key points. For example, you need to find this point in order to find the height here. You also need these 2 points to find the base here and also the base of these 2 triangles, right? So so basically it looks like it's like a coordinate geometry question, right? Okay. So anyway, how can we find this point here? Okay. So we can make use of the equation of straight line here. Okay. Now because this line here we can write it as because you know that y-intercept is 1, right? So for the, let me call this L1, this is L2. So L1 here, it should be y equals to -½ x plus 1, right?
Yeah. So
Okay, so we can set y equal to 0 to get the x-intercept here. Okay, so this x-intercept should be 2, right? If you add this, and then you times 2.
yeah.
Right. So x equal to 2. And then for L2, let's write down the equation first. Now this one, we don't have the y-intercept, but we know the gradient. So the gradient is 2. So 2x plus 1 plus 0, sorry, not plus 1, plus c. And then we plug in this point. Oh, okay, I forgot to put down the time here. Okay, let's say this is time 10. Okay. So this straight line here passes through 10, 1. Okay. So 1 and then 2 times 10 plus c. So c here is -11. So that means L2, it has an equation 2x minus 11. And now,
sorry, why is it 11?
oh, sorry, not 11, right? It's 20 here, right? Sorry,
Yeah.
it's 19. Okay, 19. Okay, so now we have this equation here. We can find the x-intercept right here. Okay, so if we set y equal to 0, that's 2x minus 19. So x is 19 over 2, which should be 9.5, right? Is it okay here?
Yeah.
Okay, and then we also need to find this point here. Okay, so for this point, we just solve these 2 equations. We have 2 equations, right? this one and that one. So if we solve the simultaneous equation, that would be a half y equal a half negative half x plus 1, and then that's equal to 2x minus 19. Okay, so if you solve this equation, let's multiply both sides by 2. So you get negative x plus 2, and then 4x minus 38. Okay, so at 38, and then if you plug in to the right hand side, that will give you 40. And then if you add this, this will be 5x. So x is equal to 8. Okay. But the main point is we want to find the y coordinate of this point, right? So to put this back to either one of these equations, maybe I'll put it here. So y is a half times 8 plus 1. That's equal to negative 4 plus 1, so negative 3. All right, so we have found all the information we need. So this one is negative, so the height is 3. And then this point is 2. This point, another point here is 9.5, okay? So the total displacement here, first of all, the first journey here, it should be 1 times 2 divided by 2, right? So the displacement is a half times 1 times 2. And then for the middle part here, you need to subtract this part, okay? So negative of a half times 9.5 minus 2, and then times the height, which is 3. And then finally add the triangle right here, okay? So it should be a half times 1 times 0.5, okay? Okay, so this one we can use the calculator to find this. 1 minus 0.5 times 7.5 times 3 plus this is 1/4, so negative 10 meter. Okay.
Yeah.
So most of the part of this question is just like a coordinate geometry question, but then you have to be extra careful about this one because it's negative right here. Okay. All right. So that's the so two types of graph you have to know. Okay, the velocity time graph and the displacement time graph. Okay. All right. So that's all about this part. And next part, we're going to discuss the constant acceleration formula. Okay. So maybe let me write down all of them at once. Okay. Okay. So remember our assumption here, the constant acceleration formula. The assumption here is we have constant acceleration. Okay. Which means that if your object does not have constant acceleration, then you don't have a, for example, you can't apply all these equations. Okay. Okay, so before talking about this formula, maybe let's talk about some situation in which there's no constant acceleration. Okay. In what situation will there be no constant acceleration? Well, for example, if your speed is changing, then obviously it's not the acceleration is not constant, right? For example, changing speed. Then there's no constant acceleration. Now, actually, there are another situation in which there's constant speed but no acceleration. Okay, Now remember, because acceleration is kind of like it has a direction, right? So somehow if your acceleration is changing in direction, then the object do not have a constant acceleration as well, right? Okay, so what kind of situation will we have? For example, your object is going through for example, you have this is the road, and then it looks like this, and then your car is going like this, okay? Now in this case, your car is changing direction, so it doesn't have a constant acceleration as well, okay? Is it okay for you?
Yeah.
So remember, if you have these situations, then you can't apply this constant acceleration formula, okay? And let's again, for now, we refine ourselves on the real line only, okay? So your object is going in a one-dimensional manner, okay? So now let's write down the formula here, okay? So we have a few formula. The first one is, let me just write down the notation first, okay? So T stand for time, U stand for the initial speed. Now the notion of, by the way, the notion of initial speed is a little bit subtle because it depends on the moment you're talking about. For example, let's see some example later, okay? So this one is a little bit subtle. But let's accept that this is initial first, okay? And then v is final velocity. Sorry, not speed, sorry. I wrote velocity, should be. This final velocity. And then what else? We have S, which is the displacement. And then finally, A is our main character, which is the acceleration here, which is supposed to be constant, okay? All right, so once we have these notations, let's write down, there are actually 5 formulas which can net off these quantities, okay? So let's find it. Let's look at them one by one, okay? So the first equation is V is equal to U plus AT, okay? So actually, well, where does it come from? Okay, so basically it comes from the fact that A is V minus U over T, okay? So you just try to rearrange this equation to get this one, okay?
Yeah.
Is it okay? Okay, all right. So and then another equation is S equal to U plus V over 2 times T, okay? So how can we have this? Okay, so as I mentioned, we have constant acceleration, meaning that our velocity time graph would look like a straight line like this, right? Constant acceleration. So for example, remember the area under the graph gives us the displacement. Okay, so if you look at this diagram here, for example, this is U, this is V. Okay, this is the initial velocity. Sorry, I think I made a wrong label here. Okay, so it should be this one. This one is U. Okay, this one is V, and then this is over a time interval T. Okay, all right. Then the area. So you can derive that this is just S, right? So you can derive this formula out of this diagram. Okay, just find this the area of this trapezium. Is that okay?
Yeah.
All right. And then third equation is V square equals to U square plus 2as. Okay, so this one you can try to derive this. Okay, so basically it comes from the equation above here. Okay, 1 and 2 will imply 3. Basically, the idea of the proof is you try to eliminate the t here, because this equation don't have t, right? So eliminates t in 1 and 2. And then you will get this equality 3. And then number 4, s equal to ut plus half at squared. Okay, so this one I think it's difficult. It's more difficult to explain why. Okay, actually it's basically comes directly from 1 through integration, but you haven't learned integration, so maybe you will see why later. Okay, but then for now we just remember all these equations. Okay, so integration of 1. And then finally we also have s equal to vt minus half at squared. Okay, so this one again you can basically you from 4 plus 4 equation 4 here and equation 1 here, you can get this equation. Okay, so it comes from equation 1 plus 4. Okay, now can you understand this equation now? So,
Yeah.
I mean what how they are coming from. Okay, so at least you have a sense of how they come from. So why do we have so many equations? Okay, so why don't we just use why don't we just use the previous method to find things? Well, because we don't usually we don't want to like draw a very complicated graph to calculate things. Using all these, we can find the other parameters. Like, for example, if I give you for example, equation number 3 here, if I give you the initial velocity and the final velocity and the acceleration, you will be able to find the displacement. Okay, so the idea here is given 3 of the variable, and then you find the rest. Is that okay here?
Yeah.
So you need to pick the equation very carefully. For example, if I only have u, t, and a, I can't really apply this equation because this equation here don't have time. And then if we only have u, t, and a, then we only have u and a here, but no v and s here. So we can't really solve 2 equations, 2 unknowns here because we only have 2 equations. And most of the time we will try to prevent the situation of solving 2 equations, 2 unknowns. Because that sometimes that will be too complicated. Now, I'm not saying that you won't face those situations. I'm just saying that as soon as you can use one of these equations, you just use one of these, but not 2 of these. Okay, yeah. All right. So that's the whole idea towards this 5 formula. Okay, so let's look at some example of applying these equations. Okay. All right, so first example. So we have a cyclist, and then it travel along a straight line. And then first of all, it accelerates. So she accelerates at a constant rate. From a velocity 4 meters per second to 7.5 meters per second in 4 seconds. Okay, 40 seconds. Sorry. So that's the condition given, and then part A, we want to find distance travel. And then the second step, the second part is to find the acceleration. Okay. Okay. So this one we need to identify the parameters coming from the above equations. Okay. So here the cyclist first of all has an initial velocity of 4, right? So that means u is 4, and then v is 7.5. Now mind the unit, okay? Mind the unit. So here we should, for example, distance we keep on using meter, and time we keep on using seconds. Okay, if they are not in those units, you need to convert it into those. Because otherwise, for example, if this is given by km per hour, and this is given by seconds, then you will get something wrong when you apply the parameters into these equations. Okay, so can be consistent about the unit. All right, but back to here, we have u equal to 4, v equal to 7.5, and then the t is 40. So we have these three. So our strategy is to find one of these equations which only have the distance or the displacement as the unknown. Okay. So here, let's look at, we have u, v, and t. So I think this one should be suitable, right? Yes, you have the initial velocity, you have the velocity, final velocity, and then the time. So we can use this, okay? So usually what we do is we write down the equation first. So this is the equation I pick. Okay. And then after picking this equation, we just plug in all these parameters. Okay. And then so this is 4, this 7.5. Oh, sorry, no. I think we need the displacement, right? Right, I picked the wrong one. Maybe I should take this one, right? Because I have u, v, and t. I want s. Okay, so s equal to u plus v over 2 times the time, and then s is unknown, and then u is 4, v is 7.5, and divide by 2 times the time, which is 40. Okay, so this one, it should be 40 times 4 plus 7.5, which is 230 meters. Okay.
Yeah.
So you pick once you have picked the correct equation, you should be able to get the answer right away. Okay, and then B, the acceleration. So just now I picked the wrong equation because I just look at part B. Okay. All right. So anyway, so we picked the equation V equal to U plus AT. Okay, and then we use all these parameters. So 7.5 equals to 4 plus AT. So A this time is 7.5, so 3.5 divided by 40. So it is 0.0875 meter per second square. Okay.
Yeah.
All right, and then or you can use another method because you have found the displacement here, right? So you can actually use any of these equations, right? Because once you have 4 parameters, basically you can use all of these equations. I think I accept this one, right? Yes, this way don't have acceleration. Or once you have 3 of these parameters, you'll be able to get all the others, right? Okay. So another, for example, we can use number 4 here. We have U, you have T, you have A. You can off. Sorry, you have S, you have U, you have T. So you can find the A as well from number 4. Okay. Is it okay for this question?
Yeah.
Okay. All right. So maybe let's end the lesson by doing one more example. Okay.
Yeah.
Okay. So for example, we have a particle. Okay. So maybe let me draw the picture. Okay. So you have a particle. Let's say it's initially at rest. Okay. And then it goes to a point. And then the speed here is 4 meter per second. Okay. And then obviously constant acceleration. And then, for example, and then it goes to another point where your speed is 5 meter per second. Okay. And then let's say the total time taken here is, for example, let's say this is the total distance travel is 2 meter. Okay. And then the time taken is, for example, T. And then what we're going to do is we want to maybe the time taken should be maybe 10 seconds maybe. Okay, so our task is to find the initial distance travel here. Okay. All right. So how can we do this? Okay. So first of all, we know that if this is x, this is going to be 2 minus x, right?
Yeah.
Okay. And then let's say so the condition given here is the time taken is 10 seconds. Okay. So that means the time taken here plus the time taken here is 10 seconds. Okay. So let's find the time. Let's start a time in terms of x. Okay. And hopefully we can solve for x using this time. Okay. All right. So this x here is the displacement, right? So for the first journey, t is what we want, and then we know s is x, and then u is 0, b is 4. Okay. So we can express this time in terms of x now, right? Because remember we have, let's look at the equation above. So we have s U and V, remember. So if you have S, U, and V, you can use which one? You can use number 2, right? S is half of U plus V over 2, and then T. Okay, so S equal to U plus V over 2 times T. So that's exactly equal to 0 plus 4 over 2, and then times the time, which is unknown. Okay, and the S is, let me put it in another line. Okay, X equal to 0 plus 4 over 2 times the time, which is unknown. Okay, so the time in terms of X, it should be half of X, right? Is it okay here?
Yeah.
Okay, again, for second journey, we use the same track here, okay? So for the second journey, again, we use S equal to U plus V over 2, T. And now we know this time is not the final velocity. This time is the initial velocity for this journey. So that's why I was saying that it was subtle about the initial. This is depends on what you're saying, okay? If you're here, if we're talking about here, then this is the initial. If you're talking about here, this is the initial, okay? So again, S here is 2 minus X, U is 4, and then V is 5, okay? And then, so you get 4 plus 5 over 2, T equal to X. So for the second journey, the total time should be, this one is 9 over 2, so 2x over 9, okay? So now we have found the total time for the 2 journey. The total time should be a half x plus 2x over 9, and that's equal to this time here, which is just sorry, this time here, which is 10. Okay. Okay. And then we can solve for the x here. Okay. So this one, I think a half plus 2 over 9, and then 10 over answer. So it's around like 13. Wait a second. Sorry, no. This is not x, right? This is 2 minus x. So this one is 2 minus x. So this one is 2 minus x. So you can solve for the x here. Okay. So this one you can multiply by 18. We have right hand side to be 180. The left hand side is 9x plus 4, 2x minus x. So this one is 8 plus 5x equal to 180. So 180 minus 8 divided by 5 is
34.4.
okay. I think there's some question. There's some problem with the question. So I think I said this one to be too short, right? So this is absurd, right? Because this 2 minus 34.4 is negative, right? I think I make this distance too short. Anyway, that's basically the strategy you need to know, right? Okay.
Yeah.
All right. So any questions so far for these equations?
No.
No. Okay. So if there's no question, then maybe let's end the lesson here. Okay.
Yeah.
All right. Okay. Bye.
Thank you. Bye.